Hello, I'm Umnik. I will solve first educational round 147 and I'll try to explain what I'm doing. In problem A, we are given a string of length at most 5 that consists of digits and question marks. Positive strictly greater than 0 integer matches the string if we can replace question marks by digits and get a representation of that number in decimal system without leading zeros. So basically the first digit must be non-zero and every other digit can be anything. And we ask to calculate the number of numbers that match the given string, and we should check if the first digit is if it is 0, then the answer is just 0. Otherwise, for every question mark we multiply it by 10, except for question mark on the first position, in which case we multiply it by 9. If the first digit is 0, just return 0. Otherwise, we say that answer is 1. And if we encounter question mark, we should multiply the answer by 10, except in the case when it is the first digit, so I is equal to 0, in which case we multiply it by 9. Problem B. An array of n integers, sort segment in non-decreasing order. Okay, so somebody sorted a segment. We are given the initial array and the resulting array after the operation. We need to find the longest such subarray, that if we sort that subarray in first array, we will get the second one. And it is guaranteed that the answer exists. So we don't have to check that the multiset of numbers is the same. We'll just look at the leftmost and rightmost positions that are different in A and A prime, so they must have changed, so they must have been inside the segment. And it is guaranteed that there is at least one such position. So we can say that we know that this subsegment is surely inside our segment, and then we can try to move left border to the left and right border to the right if in the resulting array that segment is still sorted. So we can move left border to the right if, well, there is where to move, so we're not staying in the first element, and the previous element is not greater than the current leftmost element. Yeah, because the segment we choose must be sorted in non-decreasing order in the resulting array. And we can do that independently for left and right border, because we know that there was at least one element in our initial array. And thus we will get the longest array. If the elements on position I are not equal, then we should update L and R. L we should update just in the leftmost, so only if we have not updated it yet. And in R we want the rightmost, so just write that one. The last update will be the rightmost one. We know that we should find something. Now, while the left border is not in the first element, and in the resulting array the previous element is not greater than the current leftmost, we can move left border to the right, and the same thing for the right border. This problem would be a bit more annoying if we were not guaranteed that the answer exists. Not much harder, but annoying. Problem C, we have a string. In one operation, we can select one or more positions. Just know two selected positions are adjacent, then you remove the letters on the selected positions. The resulting parts are concatenated. What is the smallest number of operations to make all the letters in S the same? So if we fix what is the letter that we want to get in the end, then we don't have to remove any letters that are equal to it, but we have to remove everything else, and so we will have those like segments of consecutive letters that we have to remove. They are independent, and like we can do them in parallel, so we need to calculate the answer for every such segment and take maximum of them. And the answer for segment should be like k, where 2 to the power of k is the smallest power of 2 that is strictly greater than the length of the substring. Because like on every operation we can remove like every other symbol, but starting from the first one, so it's like rounded down. If we have 5 symbols, we can remove first, third, and fifth. So we remove 3 and left with 2. And then we remove 1 and in the end 1. So it's like the number of times we have to divide the length by 2 rounded down to get 0. And that is the smallest power of 2 that is strictly greater than the length. Okay, how to implement that? Like I will, for all the characters, I will store the positions of all the occurrences of that character, including like imaginary occurrences in like -1 and n. So in the borders, and so like every substring I have to remove is a substring between 2 consecutive occurrences, and that will work in linear time in total. Well, I guess linear plus the size of the alphabet, because like we have multitest, it's kind of important. So like after I pushed all the positions, first I just say that we have -1, then push all the positions in order, then push position n, and now I want to try, assume that this will be the symbol that stays, then like current answer will be the maximum of answers for all the segments. Now I iterate over the segments, and for each segment, like this is its length, and I want to find the first power of 2 that is strictly greater than this length, and update the current answer with it, and then update the answer with minimum of answer for this character, because I can choose which character I will use. Problem D. We have a very long strip of cells. Yes, all of them are white initially, I assume, because the name of the problem is black cells, so probably we will have some black cells. They're numbered starting from 0 left to right, controlling special pointer in cell 0. A shift button that you can press and hold. 3 actions. Move the pointer to the right, press and hold shift button, and release shift button. So like you can start holding and release. The moment you release shift, all the cells that were visited while shift was pressed are colored in black, but we can move only to the right. Of course, you can't press shift if you already hold it. Yeah. Your goal is to color at least K cells, but there is a restriction. You're given N segments. You can color cells only inside these segments. What's the problem? Isn't it true that I should just color first K cells? The segments are disjoint, like it is guaranteed that there is a cell between the right border of the previous one and left border of the next one. So like between the segments we can color. There are white cells, so we cannot merge segments, and we can only move to the right. Oh, but to color, we will reach some point in the end, and all the colored cells should be to the left of that point. And the cost, like the number of these operations, like when we move to the right, is just the position which we reach. But also to color each segment, like I need to spend 2 operations, right? Like I need to start coloring it and then end coloring it. So if, for example, I have like one cell, segment of length 1, and then very long segment, and I want to color 2 cells, it is better to skip this first segment, and like we will have to move one further, but we will only use one segment. Yeah, so that's cheaper. Okay, but there is a solution that just takes K leftmost cells, and it will spend the least on the the operations of the first kind, and like at most 2n operations when we start and finish, like at most n of each. So it doesn't make sense to go further than like this case cell that we can color plus 2n, because the only like this moving part will be more expensive than just using the greedy solution. Okay, but then we can probably like try all the like all the possibilities to do that, right? Like there are just 2n of them, so the sum of n is bounded because it's size of input. So we can try all the options. Like we find what is the case cell that we can color, and then we can like try move one by one 2n times and try to update the answer. To update the answer, I need to understand what is the minimum number of segments I can choose so that the sum of their lengths is k, or like at most, at least k, because well, I can kind of like choose choose everything, kind of. Okay, it seems like I should be able to like maintain a multi-set of available lengths and the sum of lengths of segments in that multi-set. And if I can drop the smallest of them while keeping the sum of lengths to be at least k, then I should just do that. Yeah, so like there will be one special segment through which I iterate. Like its length will change because I'm moving like where I cut off, but all the previous segments are like they're fully traversed, so they will not change anymore. So we will not put like we will look at this special segment separately. But we will maintain well, if we can drop some segment, we will do that. In which case we can drop a segment. Well, we need to make sure that it is not needed anymore. So like without it, we have enough length, but also we need to make sure that it is not more profitable to drop the current segment. So if current length is at least the length of the small segment and sum of lengths including the current segment is at least k, then we can drop the smallest segment from the set. That should work. need to be careful while implementing it, but in general it should work. This will be a big place for like getting wrong answers. The infinity is not 10 to the 9th, because we can spend 10 to the 9th moves and also 2n operations on like pressing shift button. So we can be sure that the answer is well, if it is possible, then the answer is at most like max coordinate, which is 10 to the 9th plus 2n. So I will write it like this. Now this infinity is surely strictly greater than any actual answer I can get. So in the beginning, I just iterate over the segments like until I will get some that is at least k. So if I run out of segments but the sum is still less than k, then it's impossible, I just print -1. I don't like inclusive intervals, so I guess I will increase the right border, so the right border is not inclusive now. Then the length is just the difference. Okay, so now since I exited the cycle, sum is at least k, and I am assuming that k is still strictly greater than 0, so pos should be strictly positive. So I should like roll back the last action, because like I actually need to stop somewhere in the middle of that segment. like if I reached the end point okay, I guess this is last. Don't like to have to write -1s, but like somewhere I will have to, I guess. So this is the last point of the segment. I know that before the segment the sum was strictly smaller than k. So if I make like current sum minus k steps back, then I'm still inside the segment. Yeah, and now I actually want. All right, I wanted to insert lens here, and so from now on I want sum to be the sum of segments that are stored in the set, and we can actually update the answer with something. So I need to reach point X, and I need to spend 2 times the number of segments, but that's the size of set. Or actually it's plus 1, I guess. But look, that's kind of the more right way to write this. Okay, now remove length of the current segment from sum and from set. Okay, and now I will try to increase x while it is smaller than the current answer, because the value with which I will update is x plus something non-negative, actually strictly positive. I cannot use 0 segments. So while x is smaller than ans, I can increase x, and if it is still inside current segment, so what are the cases? X is inside the current segment, or I could have reached the end of the current segment, and here I need to say that this segment is now ended and it is like fully available. So this is the simpler case. Like here I don't have to update answer, and like if I'm not increasing the number of cells I can use, then I don't have to update the answer. So I will have to update the answers only here. Okay. Here on the other hand, I'm saying that I should increase the sum by the length. Insert the length in the set. actually, like if pos is n, I can just break. I will not find anything good in the future, but I guess that doesn't matter. Like, I don't know. Like, I will check this, which doesn't make sense if pos is n. Alright. And now I want to like fix my set by saying the following, like while true, basically. We will look at the smallest element in the set, and if removing it will still leave us with the sum that is at least k, then let's do that. Like, I cannot reach empty set here because I know that the sum should stay at least k, and k is strictly positive. Alright, now here I have increased x, so the length of the current segment is x minus a plus 1. And well, I should kind of do something like choose the best thing, like the best set of segments using this one, which is not inserted set. To do that, I will again like try to remove useless segments, but here I can do it only if okay, let's say not empty here because I will take some plus len. But yeah, I can do it only if it is not better than the current segment, because maybe I should drop the current segment instead. And some plus len minus this length is still greater than k, then we can remove it. Actually, yeah, this is bad, like this is while true without any breaks. That's not good. I should say like else break, and here. Alright, so now I know that I cannot drop anything from the set, so I'll take all of them. But if it's not enough, so sum is strictly smaller than k, then I should also use the current segment. And so I should update the answer with x plus 2 times size of the set, plus 1 if sum is smaller than k. And if I don't do any of that, if I just like print answer here, yeah, it doesn't work even on the sample. Cool. problem E looks like about bracket sequences. We are given a regular bracket sequence. In one move, we can remove a pair of adjacent brackets such that the left one is an opening and the right one is a closing. So remove like open close. Then concatenate the resulting parts. So it still will be a regular bracket sequence. The cost of this move is the number of brackets to the right of the right bracket, like to the right of this pair. Okay. The cost of the regular bracket sequence is the smallest total cost of the moves required to make the sequence empty. That sounds like sum of balances or something, like sum of values of balance for all closing brackets should be. Actually, you're not removing any brackets. Instead, you're given a regular bracket sequence and integer key. You can perform the following operation at most key times: extract some bracket and insert it back at any position. After all the operations performed, the bracket sequence has to be regular, and we are given a regular in the beginning. Okay, what is the smallest possible cost of the resulting regular bracket sequence? The number of operations is small, at most 5. Okay, so let's prove the things that I said. We can look at the regular bracket sequence as like this graph of balances. So it's like open, open, close, open, open, close, 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 open, close, open, open, close, open, close, close. So we start at balance 0 and we never go lower than 0. And the operation we do is to choose this thing and remove it and glue together these 2 points. And the cost is the distance to the end. Let's just each time choose the rightmost, like the cheapest one. The rightmost such points means that after that there are no places where like this thing happens, but that should mean that we should only go down from there, because well, if we go up at some point, we will have to go down at some further point, and at first such point that means that we just go up and then down. So we found this thing. And look that our operation like doesn't change the height of any such structure. So for this thing we will have to pay at least its height, like balance 1. So we will pay 1 for this and 1 for this, then 0 for this thing that will be created. 0, 2, 1, 1, 0. And it is just like for every pair balance. So that's the minimum we have to pay, and it is achievable just by choosing the rightmost thing every time. Okay, so we are interested in minimizing, right? What's the smallest possible cost? So we are given a regular bracket sequence. K times we can take some bracket and insert it in some other place. So we can split this operation into two parts. First, like take it out, then insert. But then it's okay if we first take out all the k brackets we are going to take out and then insert them in some order. So we can take out k brackets and then insert them somewhere. What will happen when we do that? What is happening with bracket sequence when we just move one bracket somewhere, for example, and move this closing bracket like here. So it was here, we will move it here. So for all, like we will take this part and instead of going down here, we will first go down here, but then just copy this thing, right? So, and we will arrive at the same point. So we can take this thing and lower everything else. So if we take closing bracket and move something, if we move it to the left, then like everything, every part of this graph between them will be moved down, and this thing will also be moved somewhere. We should also, that was not a great example because like these points are on the same height. But if I move it here, for example, like we will still get this thing, and so we will move this thing one down, but this part will remain here. Okay. And I want to minimize the sum of balances of, for example, closing brackets. Yes. We could also like imagine it like removing a bracket at most k times, but then inserting again like k brackets, so that the resulting is still a regular bracket sequence. Because the total balance should remain 0, we will remove and insert the same number of opening brackets, and like we could have done it with moving, but then it should be possible to like do just dynamic programming um, where I'm staying in the string, what number of uh, deletions I already used, what number of inserts I already used, and what is the current balance. It seems like the balance can be very big, but actually, like if I know what is the point where I'm standing it in right now, then I could have removed only k brackets from like until this point and inserted only k brackets. So the balance cannot change by more than 2k in uh, both positive and negative direction. And actually, like we can only care about states where it changed by at most k, because otherwise we won't be able to come back to zero in the end. Um, so that just works. Seconds. So it's n times k cubed, right? Like in the state we have a length of the prefix, number of removals, number of additions, and the change in balance, which is from minus k to plus k. Well, I think it should be fast enough. Like, k is up to 5, so like even by allowing it like 2k, so it's 5 times, well, 6 times 6 times 11, and we have like some transitions to consider, but it's still reasonable number, I think. So the answer can be like n squared. So we have to use long longs. start at 0 removed, 0 added, and current balance is on the same as in current position. So the distance is 0, but I don't want to use like negative indices, so it's like k plus 0 kind of. Okay. So that's number of removals, number of adds. First, I need to allow myself to add brackets in this position before taking the next bracket from the string. I can add opening bracket always. Yeah, let's also check that the balance at which we're looking, which is balance in position P plus the shift we did, is non-negative right now. So I can add an opening bracket, which will mean that x doesn't change, y changes by 1, d increases by 1. So we should do that only if d is strictly smaller than k. And this dp we should update with dp value, and yeah, I guess I will calculate the sum of balances of opening brackets, because for opening bracket I calculate the balance before I change it. So the current balance is this. Okay, and now if d is greater than minus k, and I will not go into the negative balances, so like current balance is strictly positive, then I can add closing bracket. Okay, now transitions that actually do something with the next bracket from the string. Since I have to only start 2 layers of dynamic, I need to fill everything on the next layer with infinities. we can either take the next bracket or skip it. Skipping is easier if, but we can do it only if we have skips left. So if we have skips left, then we should update dp1 x plus 1 y. Here should be the shift in balance, but not with like relative to position, the balance in position p, but relative to the balance in position p plus 1. Since we skip the bracket, the balance will actually change. And we can say what is the next change here actually. If we skip an opening bracket, then like the baseline increased but our balance stayed the same, so we need to decrease our shift, otherwise increase. And if it became, so we should do this transition only if it is still in bounds. And the cost doesn't change because well, we didn't change the prefix or string, like we didn't add any brackets. All right, now if we do take this bracket, then the cost might change. If it was an opening bracket. And also like the balance after we do that should be non-negative. So if the balance in position p plus 1 plus shift d, which will not change because like we changed our balance and baseline balance by the same value. So if it is non-negative, then we should try doing this transition. It will not change x, y, or d, but it might change the cost. So if this is an opening bracket, then we should increase the cost by current balance, which is this value, and update dp. Great, and now copy all the values to the zeros layer. Right, and actually we need to do this transition after we traversed all the string too. So we will say like not strictly less here, but if p is n, then we should stop. There is no next symbol to consider. All right. Now we should iterate over the number of moves we actually did. So what are the parameters that the parameters of dp that correspond to actual possible options. So x and y should be the same, and the balance in Z should be 0, and so the shift of balance is also 0, therefore. So it's I k plus 0. Well, it's not super fast. Time limit is 2 seconds, I think. But should be enough to get accepted. Okay, the last problem F. Some American issues. The beautiful alley with trees in front of a shopping mall has to go to make space for the parking lot. That makes sense. Okay, so we have n spots for trees. I guess like on the sum of the spots there are trees of height k, but it is not given, so I guess we will decide something. When you chop down a tree in the spot x, you can make it fall either left or right. Okay, so like either x minus k to x or x to x plus k inclusive. Let's say that we have m trees in some spots. Let an alley be called unfortunate if all m trees can be chopped down in such a way that no tree falls like outside the segment 1n. We have shopping mall in 0 and road in n plus 1. Each spot is taken up by no more than one fallen tree. So an alley is unfortunate if we can chop it off. Okay. Calculate the number of different unfortunate alleys with m trees of height k. Two alleys are considered different if there is a spot such that a tree grows in y, the first alley, and doesn't grow in y on the second alley. Okay, so after we fall all the trees, there will be segments of like each segment will cover k plus 1 possible points. Like this. So for that to be possible, we must have like m times k plus 1 at most n. But it's not true that, well, it is tempting to just say let's choose those segments, they should be no intersecting, and then for each segment we could have placed the tree in its left or right border. but it's not correct because we can calculate some three um, how do you call it, like placements of trees several times, because like we calculate the number of ways to choose trees, and for each tree to which in which direction it will fall, but we only need to calculate the number of positions of trees. All right. So if we have some sequence of trees like this, then we can greedily choose in which direction to fall them. Like for let's go left to right, and for each tree, if we can fall it on the left, do that, otherwise fall it on the right. So in this case, like we will follow this one to the right because there is not enough space on the left, and this one on the left, and this one actually we will choose this segment for it. Okay, now with this greedy, the way to fall trees is unique. So we can try to calculate the number of ways to place trees like according to that grid. Or maybe like we will place segments and choose left to right endpoint for each of them, but we have to make sure that it is with accordance with the greedy, which means that like why this was bad, because we have chosen the left point. It means that the tree was here, but there is enough space to the left here. So if we have a segment and we have chosen the left endpoint, then and like k previous points are free, then it's bad. If we have chosen the right point, it's good because we have fallen the tree on the left, and that's great. It could have happened that like there is something wrong like this. So like we have this segment, and this segment, and we have chosen the left endpoint in all three cases, and it looks like well, we cannot rotate this one because like this takes its space, but we can actually like rotate all three, so it is not the right way to draw segments for these positions of trees. But if we like find the leftmost which is not optimal, then we can just rotate it freely. So for a wrong way to choose segments and endpoints, there will be a segment that is wrong right now, that we can like rotate right now. Okay, cool. So we know m, we know k, we know n. Here are segments. Each segment takes k plus 1 points. So there will be n minus m times k plus 1 free red points left. So I'm saying that we have this many free points, and segments. Like, how to calculate the answer if we do not choose endpoints for each segment and just choose segments? Then we have this many free points, this many segments, and we just choose their order. Points are indistinguishable and segments are indistinguishable. Like, for example, for this order, we will have like first 2 points, then 2 segments, then 3 points, then a segment. And if we know this compressed order, we can uniquely restore what are the actual positions of segment because we know their lengths. And the number of ways to choose this thing is just binomial coefficient. Okay, but now how do we make sure that there is nothing bad? Like, what is bad? Bad means that we have chosen left point for at least one segment, and like there is k free points to the left of it. Okay, it seems that we should be able to apply like inclusion-exclusion principle. Okay, we need to calculate how many ways to choose the endpoint if no segment has like bad left point chosen. But what if we say that like this and this segment do have bad left point chosen? But that means that before them there is like k red points. So if we have t bad left points, then like before those segments there should be k red points. We can merge them right now and say that okay, then we have like n minus m times k plus 1 minus t times k red points left, and it should be non-negative. Then we choose their order. And now we have fixed bad segments, probably not bad segments, of which we have m minus t and 3 points. So the number will be like multinomial coefficient, which is minus t factorial and this monstrosity n minus m k plus 1 minus tk factorial, and the sum of all of that factorial. Sum of this is m, and we have m here, so it's n minus mk minus tk factorial. That's our multinomial coefficient. And also for segments which we did not fix to be bad, we can choose either left or right endpoint to be like where the tree is situated actually. So it's 2 to the power of m minus t. Yeah. Since it is inclusion exclusion, we multiply by minus 1 to the power of t and sum this up t from 0 to m, like considering that this should be non-negative. I think that this is the answer exactly, and we can calculate it in linear time. I wanted to write if n is smaller than m times k plus 1 here, but no, like that would be integer overflow. So that's it for today's education round. Interesting. I think that f is much easier than E. Maybe I overkilled E. F is very straightforward combinatorics. G is nice. C is nice. It was an okay contest. How's that? Say. Okay. Thanks for watching. Bye.